We're going to go through a few conceptual questions that involve mass spring systems. So we know a mass on a spring can oscillate. So again, try answering these questions on your own or answer it, and then watch the solution to make sure you understand the correct answer. So here is our first question. So the correct answer here is A. So we have a mass on a spring. We take the mass and we pull downwards on the mass. By doing this, we increase the elastic potential energy. The spring's energy increases because we're now stretching the spring even more. The gravitational potential energy does decrease, but it does not decrease by as much as the spring's energy increases. And that's because that stretching distance is squared. Another way to think about this is that we have to put energy into the system, give it more mechanical energy to allow it to start oscillating. So more potential energy. So the sum of the potential energies is the total energy. That increases in this case. Here we have another question. What do you think about this one? So the correct answer here is C. They tell us that 0, O, is the relaxed or unstretched position. That means that's equilibrium. E is the maximum distance, so the amplitude. M is somewhere in the middle. We know the acceleration is a maximum when the displacement is a maximum. And that's because the force of the spring depends upon the displacement. So that force gets bigger and bigger until we reach a maximum distance, and it's the force that causes the acceleration. So point E is where the acceleration is the maximum. All right, here is another question. What do you think about this one? The correct answer here is B. So if we have identical masses, they're given the same speed at the origin, that means we've given them somehow the same kinetic energy. At the origin, meaning the equilibrium position, the energy is all kinetic. That's why I'm writing that as a V max. We know the kinetic energy turns into potential energy. And so if they have the same kinetic energy, they must have the same potential energy overall. But if they have different K values, then they have to have different amplitude values to in turn have the same value overall. So to get a big amplitude, we need a smaller K. So a smaller spring constant to get a larger amplitude. So that's why the floppy spring, meaning the weaker spring, is going to have a larger amplitude of motion. Here's another question. What do you think about this one? So the correct answer is C. We know for a mass on a spring, omega is the square root of K over M. But again, omega is 2 pi F. F is 1 over T. So the period will be 2 pi over omega, which ends up being 2 pi times the square root of m over k. So in terms of determining the period of this system, it's the mass and the spring constant that determine the period. Amplitude does not determine the period. Now, amplitude, if we think about an equilibrium, a mass pulled to A versus a mass pulled to 2A, this one has more energy, which means as it moves and passes through equilibrium here, this mass would travel a lot faster than this one. But they go through their entire oscillation in the same amount of time, which is maybe a little confusing. So the period means they complete an oscillation in the same amount of time. On average, this bottom one is just going faster over that time period than the top one. So it has a higher maximum speed, which allows it to travel faster overall. But the period ends up being the same. I have another question here. What do you think about this one? All right, I'm going to reason through this one because I need to in order to ensure I'm getting the right answer. So we're essentially doubling the mass. In the previous example, we found the period of a mass spring system ends up being 2 pi times the square root of m over k. So by gluing an identical block on top of the original one, we're essentially doubling this mass. What I want to do is to factor out this portion and see what I'm still left with. What I'm still left with is the original period. And so my new period is the square root of 2 times that original period. So the correct answer is D. All right, we have a couple more. So this one, what do you think here? The correct answer here is B. So this mass on the spring is oscillating between some point A and some point B. So points A and B are the turning points. It's where momentarily the mass has come to rest and is turning around to head the other direction. So if we think about oscillations, they would look up and down on the graph. We know that the speed is maximum when the mass passes through equilibrium. Here, though, it wants to know when the kinetic energy is a minimum, meaning essentially 0. So that would be happening at the turning points, A and B. If it had asked for the maximum kinetic energy, we would say midway between A and B, because that's where the equilibrium would be. All right, one last conceptual question here. What do you think here? The correct answer ends up being C. So if we think about the total energy, At the moments in time when the mass is at its maximum displacement, all of the energy is potential energy. So we can write that as 1/2 kA squared because A, the amplitude, is the maximum displacement. There's moments in time when the energy is maximally kinetic. Everywhere else in between, it is a mixture of kinetic and potential. So we're essentially saying we have a portion that's kinetic energy and a portion that's potential energy. So this potential is potential. This piece is potential. This piece is kinetic. So we're trying to figure out how much this kinetic is. So they're telling us that x, the actual displacement at that moment in time, is half the amplitude. I'm sorry, I'm starting to square it because I'm jumping the gun. That means the potential energy, 1/2 kx squared, if I plug this 1/2 a in, I get 1/4, so I'm just squaring the 1/2, and that's leaving me with 1/4 times 1/2 kA squared. 1/2 kA squared is the total overall energy, the mechanical energy of this system. So at this moment in time, the potential energy is 1/4 of the total energy. But the potential energy plus the kinetic energy have to add up to be the total energy. So if this is 1/4 of the total energy, this has to be 3/4, the rest of it, so that they add up to the total. And this is why the fraction of energy is kinetic is 3/4.